long before satellites whispered signals across the sky, long before clocks pulsed with the regular rhythm of cesium atoms, human beings tried to answer a deceptively simple question. Where exactly are we? The answer might seem obvious if you point to the ground beneath your feet, but for travelers, for sailors, and for astronomers looking upward, the question becomes much harder. For thousands of years, people built their understanding of location out of what they could see with their eyes and measure with simple tools. Their systems of knowing were rough, often poetic, and sometimes startlingly accurate. The oldest markers of place were often carved in stone. Great monuments were aligned with the rising or setting of the sun at solstices, or with the familiar constellations. These alignments were not only ceremonial, but practical. They showed that location was connected with cycles of time. To know when the sun would rise at the same point on the horizon again was to measure both time and space together. From the megaliths of Europe to the Great Pyramids of Egypt, this ancient knowledge showed that people tied their sense of position to the heavens. Yet it was not until the Greeks that geometry gave real precision. Eratosthenes, working in the 3rd century before the Common Era, used a simple stick, shadows, and a deep well to measure the size of Earth. At Syene, which we now call Aswan, the sun stood directly overhead on the summer solstice, while in Alexandria, it cast a shadow. By comparing the angle of that shadow to the distance between the two cities, he calculated the circumference of Earth with remarkable accuracy. The method was ingenious, but it also highlighted the connection between local observation and a larger geometric frame. To find where you are, you must imagine yourself on a sphere. For centuries, sailors ventured across seas with nothing more than landmarks, the height of the pole star, and dead reckoning. Latitude, the measure of north and south, was relatively easy to find. One only had to measure the angle of the pole star above the horizon. But longitude, the measure of east and west, was a torment. A ship could drift unknowingly hundreds of kilometers off course because there was no reliable way to measure longitude at sea. The oceans were graveyards of wrecked ships and lost fortunes, all because sailors could not answer exactly where they were on the globe. The breakthrough was time. If one knew the exact time at a fixed reference point, such as Greenwich, and compared it to the local time on the ship, then the difference would reveal longitude. But that required a clock that would keep accurate time over long voyages, through storms, across temperature changes, and with no resetting by land. Early attempts failed. Pendulum clocks faltered on rough seas. Astronomical tables based on the transit of Jupiter's moons were ingenious but impossible for ordinary sailors. Into this challenge stepped John Harrison, a self-taught English clockmaker of the 18th century. He built a series of marine chronometers, culminating in his H4, which was small, resilient, and astonishingly accurate. With Harrison's chronometer, sailors could finally keep time well enough to determine longitude within a few kilometers. The age of global navigation had begun, and with it the modern idea that where you are on Earth can be written as a pair of numbers, latitude and longitude, tied to a reference meridian. Yet even that raised disputes. Which meridian should count as 0? Different nations argued for their own capitals. French maps placed the prime meridian through Paris. The British pressed for Greenwich. It was not until the late 19th century that an international conference finally agreed to make Greenwich the standard. By then, railways and telegraph wires had already demanded synchronization of time and standardization of maps. Where you are and when you are had become matters of international agreement as much as local measurement. But the drive for greater precision did not stop with Harrison's clocks or with Greenwich. In the 20th century, astronomers began to connect telescopes across continents, using a technique called very long baseline interferometry. By comparing signals from distant quasars, they could measure the tiny difference in arrival time at different observatories. This required atomic clocks to keep time at the level of billionths of a second. It also allowed Earth's position to be determined with an accuracy no sailor could have dreamed of. The same principle that once linked the shadow of a stick to the size of the Earth was now expanded to radio waves crossing light years, all in the pursuit of answering exactly where we are. The lesson from this long sweep of history is that position is never just a point on a map. It is a relationship between observation, measurement, and agreement. Eratosthenes needed both Alexandria and Syene. Harrison's sailors needed Greenwich and a chronometer. Modern astronomers need radio telescopes on different continents. Every attempt to pin Earth's position leads to the recognition that location only exists in relation to a chosen frame. To ask where exactly Earth is, we must first decide what counts as our reference. And that is the key. To be precise, we must define a frame of reference. The quest for precision did not pause once sailors could find their way across the oceans. Astronomers still faced a problem as old as Eratosthenes. If the Earth is to be measured and mapped, then its place in the cosmos must also be known. One of the most ambitious undertakings was the observation of the transit of Venus. When Venus passed directly across the face of the Sun, its silhouette could be tracked from widely separated points on Earth. By timing the transit from different locations, astronomers could calculate the distance between Earth and the Sun with far greater accuracy than before. Expeditions were sent across the globe to remote islands and polar stations in order to record the precise moments of ingress and egress. This was not just an astronomical curiosity. The scale of the entire solar system, and by extension the calibration of all celestial maps, depended on these measurements. The voyages were heroic, but not always successful. Clouds could ruin years of preparation. Observers risked storms, disease, and political unrest. Still, the results of the transits in the 18th and 19th centuries brought the astronomical unit into sharper focus. By tying Earth to the Sun with numbers of increasing accuracy, humanity tightened the cosmic lattice on which all positions could be hung. To know exactly where Earth was in the solar system, and by consequence in space, required the collective effort of international teams risking lives for a few crucial minutes of observation. By the mid-19th century, the problem of global reference frames grew urgent. Telegraph networks spanned continents, trains demanded timetables, and nations demanded maps that matched at their borders. Different countries clung to different prime meridians, and maps that should have overlapped failed to align. An international conference was convened in Washington in the year 1884, and after much debate, delegates agreed that the meridian through Greenwich would serve as zero longitude. Not everyone was pleased. France clung to its own Paris meridian for decades after, but eventually, the world settled on Greenwich as the starting line for longitude, and thus, for global time zones as well. This was a triumph of politics as much as of science, a recognition that measurement requires consensus. A coordinate is only as good as the definition behind it. The 20th century transformed measurement again. Where Harrison had relied on springs and gears, physicists now turned to the fundamental vibrations of atoms. Cesium atoms, when bombarded with microwaves, tick with astonishing regularity. By the 1950s, laboratories had built atomic clocks that kept time far more steadily than any mechanical pendulum or quartz crystal. The second itself was redefined, no longer tied to the rotation of Earth, but to the oscillations of cesium. This was revolutionary. Time was no longer an accident of planetary spin, which drifts and wobbles, but a constant of physics itself. These atomic clocks gave new power to geodesy, the science of measuring Earth's shape and position, with signals traveling at the speed of light. Even a nanosecond of timing error meant a position error of nearly 30 centimeters. Only with atomic precision could distances across continents be resolved to within millimeters. Suddenly, the measurement of Earth's place became a game of light and time. Telescopes connected by radio, satellites tracked by radar, and observatories synchronized by atomic oscillations all combined to pin our planet more firmly into its cosmic coordinates. Still, every improvement in accuracy revealed hidden motions. The prime meridian at Greenwich, once the fixed reference, was shown to drift. The Earth itself was not stable. Its spin slowed due to tidal friction with the Moon. Its crust shifted with earthquakes and continental drift. Even its center of mass shifted with the flows of air and water. The more precisely one tried to say where Earth was, the more one realized that exactness was a moving target. The problem was not only measurement, but definition. What point on Earth was one actually trying to locate? Its surface, which constantly changes, its center of mass, which drifts with the tides, or its orientation in space, which wobbles like a top? This realization marked a turning point. Precision could no longer mean a single fixed answer. Instead, it meant defining a consistent frame, tied to physics, clocks, and agreement. In this way, the pursuit of exact location transformed from a sailor's practical need into a philosophical one. To locate Earth exactly, one must ask not only how to measure, but what exactly is meant by location in the first place. By the closing decades of the 20th century, new technologies hinted at answers. The technique of very long baseline interferometry matured, linking radio telescopes thousands of kilometers apart. Observations of distant quasars allowed Earth's rotation and position to be measured against an effectively fixed background. Laser pulses bounced off satellites in orbit gave yet another tool to measure the shifting geometry of Earth. And with each new tool, the reliance on atomic clocks deepened. The clocks became the heartbeat of the planet's position, ticking in unison across observatories, defining not just when, but where Earth is. The sweep from Eratosthenes' shadows to atomic oscillations shows a clear trajectory. The question of location shifted from simple geometry to global agreements to physics itself. Where once one asked which landmark or which meridian defined a place, now one asked which atomic transition, which reference frame, which cosmic signal. Each advance brought us closer to a technical kind of exactness, even as it revealed that there is no single, eternal place for Earth. The stage was set for the full revolution of coordinate systems and reference frames, where mathematics, satellites, and global networks would combine to make precision an everyday reality. The story of where we are was about to move from history to physics. By the time the first satellites rose above the atmosphere in the mid-20th century, the groundwork of centuries was ready to be tested. With a small object orbiting Earth, physicists had a new marker against which to measure. The launch of Sputnik in 1957 did more than trigger the space age. It also provided a new way to test Earth's shape and gravity. By tracking the satellite's orbit, scientists could see subtle variations in Earth's gravitational pull, which in turn revealed bulges and irregularities in the planet itself. The familiar image of Earth as a smooth blue marble was already giving way to a more complex picture, where mountains, ocean trenches, and flows of water all shifted the balance. The satellites also showed how indispensable precise time had become. To track an object orbiting at kilometers per second required timing accurate to tiny fractions of a second. Radar signals were bounced off the moon, returning after just a couple of seconds, but carrying information about distance to within a few meters. As atomic clocks improved, those meters shrank to centimeters and then to millimeters. The same principle that once allowed a sailor to know his longitude by a chronometer now allowed a physicist to know Earth's position by radar echoes and orbital tracking. It was at this point that very long baseline interferometry reached its full potential. By comparing the arrival times of radio waves from quasars billions of light years away, astronomers created a practical, inertial frame. These quasars, so distant that their tiny motions across the sky were negligible, served as fixed beacons. Against this cosmic backdrop, Earth could be located with exquisite accuracy. The irony was profound. To know exactly where we are on our small planet, one had to look out to the furthest reaches of the universe. In parallel, atomic timekeeping advanced further. Cesium clocks were joined by hydrogen masers, and now optical clocks using strontium and ytterbium promise accuracies so fine that they would not drift by a second over the age of the universe. With such clocks, position can be determined to within millimeters over global distances. Time and space, once considered separate, are revealed as inseparable partners. Without the tick of atoms, no coordinate can be trusted. Without the definition of frames, no measurement can be made. The result is that the simple question of where Earth is becomes entangled with philosophy. Do we mean where Earth is relative to the Sun at this moment, knowing that the Sun itself moves around the galaxy? Do we mean where Earth's center of mass is, or the shifting surface on which we stand? Do we mean its position in a coordinate system defined by quasars, or in one tied to the motions of the planets? Each answer is exact only in its own context. Beyond that context, it dissolves into ambiguity. And yet, this does not diminish the triumph of measurement. From shadows in a well to satellites in orbit, from pendulums to atomic oscillations, the journey shows a relentless sharpening of our ability to pin the planet into a web of relations. Each step made possible new feats. Harrison's clocks made ocean trade reliable. The transit of Venus gave scale to the solar system. The prime meridian allowed global navigation and time zones. Atomic clocks and radio interferometry tied Earth to the stars themselves. So when we ask, where exactly is Earth? The answer is not a single point written once and for all. It is a story, a history of definitions, and a chain of comparisons that reach from ancient markers to the beating of atoms. It is an agreement, a negotiation, and a physical constant all woven together. That is why this first chapter carries us from ancient markers to atomic clocks, because it shows that exactness is not found in the ground beneath us alone, but in the frames and rhythms we choose to trust. And with that, we arrive at a pivot. To move further, we must leave behind the simplicity of landmarks and clocks and enter the domain of coordinate systems. For only by defining frames with mathematical rigor can we hope to say, with any precision, where Earth really is. When a sailor in the 18th century held a chronometer and compared the ticking of its hands to the rise of the sun, he was not merely keeping time. He was connecting himself to a coordinate system. The longitude that told him where he was depended on the decision to make Greenwich the zero line, and the latitude that told him his north-south position depended on the idea of Earth as a sphere. To locate Earth exactly requires something more than clocks and shadows. It requires grids, definitions, and frames of reference. The simplest of these is the geographic system of latitude and longitude. Imagine Earth as a perfect sphere, spinning like a ball. Draw a line around its fattest part, call it the equator, and measure angles north or south from there. Draw a line from pole to pole, call one of them zero longitude, and measure east and west from that line. This is a system of pure geometry, a way to map points on a curved surface with two numbers. For ancient explorers, this was enough, but for modern physics, where accuracy must be measured in centimeters or even millimeters, the sphere is far too simple. Earth is not a perfect sphere. It bulges at the equator because of its spin, and it is dented by mountains, trenches, and the pull of moving oceans. To capture this reality, scientists define Earth as an ellipsoid, a slightly squashed sphere. The ellipsoid can be described mathematically with a semi-major axis and a flattening factor, numbers that capture its bulge. The World Geodetic System, known as WGS-84, uses such an ellipsoid as the basis for all GPS positions. When your phone tells you your location, it is computing where you are on this mathematical surface, not on the irregular hills and valleys beneath your feet. But even this is not enough. If you were to stand on the shore and ask where sea level is, you might expect it to be flat. In reality, it is not. The oceans are heaped up by winds and currents, drawn down by gravity from mountain ranges, and pushed into bulges by the moon. To define sea level precisely, scientists use the geoid, which is an equipotential surface of Earth's gravity field. Imagine covering the globe with a hypothetical ocean that is perfectly still, responding only to gravity. Its surface would rise and dip invisibly, following the variations in Earth's mass. That invisible surface is the geoid, and it is the reference against which true elevations are measured. Saying that a mountain is 2,000 meters high means that it rises 2,000 meters above the geoid, not above some flat, imagined sea. The distinction between the ellipsoid and the geoid shows how complicated the word location really is. A coordinate system must always choose what to treat as the baseline. GPS uses the ellipsoid for simplicity. Surveyors use the geoid to measure height above sea level. Astronomers use the center of mass of Earth, or even the barycenter of the solar system, as their 0 point. Each frame is precise within its own rules, But no one frame captures all meanings of position. As technology advanced, the need for global precision grew. This led to the creation of the International Terrestrial Reference Frame, known as the ITRF. Unlike a static ellipsoid, the ITRF is a living system. It is defined by hundreds of tracking stations around the world, using satellite laser ranging, very long baseline interferometry, Doppler orbitography, and GPS receivers. Each station measures its position constantly, and the combined data define Earth's geometry at any given time. Because Earth's crust shifts due to tectonic motion, and because the planet wobbles on its axis, the ITRF must be updated every few years. The version called ITRF 2020 is not the same as ITRF 2005, even though they describe the same planet. This is because the planet itself changes, and the precision of our measurement improves. The lesson is striking. What seems like a simple coordinate on a map, a pair of numbers telling you where you are, is actually embedded in a vast web of definitions and international agreements. To say that Paris lies at a certain latitude and longitude is to invoke the WGS 84 ellipsoid, the geoid model used for altitude, and the version of the ITRF that ties everything together. It is to stand on a shifting crust, on a planet that spins, wobbles, and drifts through space, and to fix yourself against all of that motion with the help of global mathematics. Even the familiar concept of sea level becomes slippery. There is no single sea level, but rather an endlessly moving ocean. The geoid provides a mathematical still water surface, but in practice, tides, currents, and climate variations constantly shift the true ocean. This means that when we say a coastal city is 2 meters above sea level, we are speaking with layers of definition beneath that statement. It is precise only because the definitions are agreed upon. To define Earth's location, we need not just a grid, but a frame, and frames demand precision timing and baselines, which is why, as the 20th century closed, the stage was set for time and light to become the ultimate rulers of space. The transition from local landmarks to global frames marked a shift not only in geography but in philosophy. Once a coordinate was just a mark on a map. Now it became an entry in a system defined by international science. When satellites and radio telescopes joined the task, Earth itself was measured against signals from the stars. Suddenly, a coordinate meant not only where you were on Earth, but where Earth was in space. The World Geodetic System, WGS 84, is the frame that underlies nearly every GPS device. It assumes Earth is an ellipsoid with specific dimensions, and it defines a global coordinate grid where any point can be described in latitude, longitude, and height above the ellipsoid. This system is not a frozen map. It is continually refined as tectonic plates move, as glaciers melt, and as our measurements improve. When your phone gives you a location, it is invoking this vast infrastructure. A few digits on a screen hide decades of geophysical work and millions of equations. Yet WGS 84 is only one of several frames in play. The International Terrestrial Reference Frame is even more precise. It is built from a network of ground stations that track satellites, fire lasers, and listen to radio waves from distant quasars. Each station provides data that are combined into a unified model of Earth's geometry. Because tectonic plates drift, each station's position must be given as a function of time. A point in California moves a few centimeters each year relative to a point in Europe. The ITRF accounts for this, creating a system where coordinates remain consistent even as the crust itself shifts beneath our feet. Above this terrestrial frame lies the International Celestial Reference Frame, or ICRF. This is built not from Earth measurements but from the positions of distant quasars. Quasars are active galaxies billions of light years away, whose radio emissions are bright and steady. By measuring their positions with very long baseline interferometry, astronomers fix an inertial frame that is as stable as the universe itself allows. The ICRF serves as the ultimate backdrop. Earth's motion, rotation, and wobble are all measured relative to it. In effect, the ICRF is the modern version of the old idea of the fixed stars. Where ancient sailors navigated by constellations, modern physicists navigate Earth itself by quasars. The link between the ITRF and the ICRF is delicate. Earth rotates and wobbles, so the orientation of the terrestrial frame must be constantly updated to match the celestial frame. This requires precise models of precession, nutation, and polar motion. It also requires time so accurate that a billionth of a second matters. Without that, the transformation between Earth-based coordinates and space-based coordinates would drift, and the illusion of precision would collapse. All of this complexity filters down into ordinary life in the form of GPS. When a receiver on the ground listens to signals from satellites, it computes distances by timing how long each signal took to arrive. With 4 or more satellites, it can solve for position and time. The satellites themselves are located within the WGS-84 frame, and their orbits are predicted and corrected daily. The signal that seems so simple on a smartphone screen is in fact the endpoint of a chain that runs from quasars billions of light years away, through radio telescopes and atomic clocks, into satellites, and finally into the chip in your pocket. This is why location is never just local. A coordinate in Paris or New York is tied to definitions that extend outward into space. When you pin a dot on a map, you are standing in a lattice defined by physics, mathematics, and agreement. The ellipsoid is a compromise, the geoid, a subtle correction, the ITRF, a dynamic reference, and the ICRF, a cosmic anchor. Together they form a hierarchy of frames, each layer binding Earth more tightly to the universe. The fascinating part is that even these frames are not final. Each new version of the ITRF incorporates better data. Each new release of the celestial frame uses more quasars and sharper radio measurements. Precision is a moving frontier. What counted as exact in 1980 is crude today, and what is exact now will look crude in the next century. But the principle is constant. To say where Earth is requires choosing a frame and agreeing on the rules. The geoid provides a vivid example of why this matters. Imagine 2 cities at the same latitude and longitude, one in the Himalayas and one at the seashore. Their heights differ not just by meters of rock, but by the way Earth's gravity field shapes the invisible surface beneath them. When surveyors calculate altitude, they must reference the geoid, not the ellipsoid. Otherwise, their results would be nonsense. An aircraft flying at 10,000 meters above the ellipsoid might in fact be at a slightly different height relative to mean sea level. Only by defining the geoid carefully can safety and precision be maintained. Thus, every coordinate you encounter is a shorthand for a choice. Latitude and longitude might look absolute, but they are always bound to the model chosen. Whether WGS 84, ITRF 2020, or some future refinement, the numbers only have meaning within their frame. And the frame itself is tied to physics, from the pull of gravity to the tick of atoms, to the light of quasars. To ask where Earth is without specifying a frame is like asking how long something is without saying what you are using as a ruler. The measure exists only in relation to a defined standard, and the history of standards shows that those rulers change. The journey from maps and grids to inertial frames is not just technical. It is a story of how humanity negotiates its place in the cosmos, with each new level of precision demanding deeper agreement on definitions. As the 20th century closed and the 21st opened, the realization deepened that frames alone are not enough. They must be supported by time, for without exact time, no coordinate can be measured. Light and clocks became the ultimate arbiters, turning abstract grids into physical rulers. The closer we look, the more we see that no coordinate is fixed forever. A dot on a map may appear absolute, but the land beneath it is drifting. Tectonic plates creep across the globe at the pace of fingernails growing. An observatory in Hawaii moves slowly northwest as the Pacific plate slides. A city in South America shifts relative to Europe by centimeters each year. The International Terrestrial Reference Frame accounts for this motion by assigning not only coordinates, but velocities. Each station in the global network has both a position and a speed, and these values change as the Earth itself shifts. To say exactly where something is, you must also say when, because the numbers change with time. This is why updates to the reference frames are essential. Each new version refines the positions and velocities of the tracking stations. The difference may be only a few millimeters, but for spacecraft navigation or tectonic studies, those millimeters matter. Imagine trying to measure sea level rise when the land itself is moving. Without a stable global frame, the measurements would be meaningless. The frame becomes the invisible stage on which every scientific drama unfolds, from climate studies to earthquake monitoring to satellite tracking. At the same time, the terrestrial frame is only one side of the coin. To relate Earth to the cosmos, we must connect it to the celestial frame defined by quasars. This connection is not trivial. Earth wobbles like a top. The axis of rotation traces a slow precession over 26,000 years, a nutation with shorter cycles and irregular shifts known as polar motion. These motions must be modeled with exquisite care to transform terrestrial coordinates into celestial ones. Without that bridge, the ITRF and the ICRF would drift apart, and our sense of location would fracture. This interplay of frames explains why sea level itself is so hard to define. The geoid, shaped by Earth's gravity, is the true reference. But the geoid is not static. It changes as ice melts in Greenland, as water moves in the oceans, and as the atmosphere shifts its weight. Satellites like GRACE measure these changes by tracking variations in Earth's gravitational pull. They show that the geoid rises and falls with climate, tides, and human activity. Thus, even the baseline of height, the thing we call sea level, is a living surface. To pin it down is to chase a moving target. And yet, despite all this complexity, we treat coordinates as if they are simple. Your phone shows a latitude and longitude, and you trust it. The map on your screen hides the web of frames, clocks, and cosmic anchors beneath. That trust is earned by decades of refinement, by international committees arguing over definitions, by physicists aligning telescopes across continents, and by satellites circling overhead with atomic clocks on board. A single pair of numbers carries the weight of an entire scientific infrastructure. The elegance of this system lies in its universality. A coordinate measured in Tokyo means the same as a coordinate measured in Buenos Aires, because both are tied to the same reference frame. Without that shared frame, maps would not overlap and airplanes could not navigate globally. The world has stitched itself together through coordinates, grids, and frames, and in doing so has created a shared stage on which all human activity plays out. But this universality comes at a price. The more precise we become, the more fragile the system grows. Millimeter errors in one part of the world can propagate into errors across the globe. A shift in a reference station due to an earthquake must be updated in the models, or else every coordinate tied to it will drift. Precision demands vigilance. The frames must be watched, corrected, and redefined as the Earth changes. There is no final, eternal coordinate system. There is only the latest, best definition, awaiting the next refinement. This is why frames are not just mathematical, but temporal. They live in time, just as Earth does. A coordinate written without a date is incomplete. It is like giving a position without saying whether the land has risen or sunk since the last update. Time is inseparable from space, even in the humble act of writing down latitude and longitude. This fact will lead us to the deeper truth that clocks and light themselves are the ultimate tools for measuring location. And so, the chapter closes where the next must begin. We have seen how grids evolved from lines on maps to global reference frames, anchored by quasars. We have seen how sea level becomes an abstract geoid, how tectonic drift demands velocity models, and how coordinates are agreements as much as they are measurements. To go further, to measure Earth's location with the highest possible precision, we must bring in the true rulers of the cosmos. Time and light are the final yardsticks, and they will carry us from the abstractions of frames to the physical reality of measuring space itself. To measure Earth is to measure distances, and to measure distances is to measure time. This connection is so fundamental that it often hides in plain sight. When a sailor checked the position of the sun against his chronometer, he was using time to find place. When radar beams bounced off the moon and returned a few seconds later, Scientists were using light and time to measure distance. At the deepest level, every ruler is a clock. Every measurement of where we are is built on how well we can keep time. The meter itself, once defined by a metal bar kept in Paris, was redefined in terms of light. In 1983, the International System of Units declared that the meter is the distance light travels in 299,792,458 parts of a second. With that single decision, the speed of light was fixed as a constant, and length became a function of time. The ruler of the universe was no longer a bar of platinum, but the tick of an atomic clock. Atomic clocks rely on the oscillations of atoms, which are as steady as the laws of physics allow. Cesium atoms, for example, resonate when exposed to microwaves at exactly 9,192,631,770 periods per second. This number is not arbitrary. It is a constant of nature, reproducible in any laboratory on Earth. By counting these oscillations, we define the second. And by tying the meter to the speed of light, we define distance in terms of that same second. The circle closes. Time and space are bound together by definition, not merely by theory. This redefinition had profound consequences for geodesy and astronomy. With atomic clocks synchronized across continents, radio telescopes could compare signals from distant quasars to within billionths of a second. The difference in arrival times revealed the distances between observatories with millimeter precision. Without atomic time, very long baseline interferometry would collapse into noise. With it, Earth's orientation in space could be measured against the fixed stars. The same principle applies to satellites. A GPS satellite carries atomic clocks that broadcast signals tied to precise time. A receiver on the ground measures the arrival times of signals from multiple satellites. Each signal is like a pulse of light, traveling at a known speed. By comparing the times, the receiver calculates distances to the satellites, and from those distances it triangulates position. The entire system rests on the constancy of light speed and the stability of atomic time. Remove either, and the network of navigation collapses. The precision of these measurements is astonishing. A nanosecond of error corresponds to a distance of about 30 centimeters. To locate positions on Earth within a few centimeters requires clocks accurate to better than a few billionths of a second. This is why the development of hydrogen masers and optical clocks is so important. Optical clocks, which use the oscillations of visible light frequencies in atoms, such as strontium or ytterbium, offer accuracies that dwarf those of cesium. They promise timing so stable that they would not lose a second over the age of the universe. With such tools, location can be determined at the millimeter level over continental distances. But this reliance on time also reveals fragility. The signals that link satellites to receivers pass through the atmosphere, where they are delayed by ionized layers and water vapor. These delays distort the apparent time of arrival. Corrections must be applied constantly, using models of atmospheric behavior or additional measurements. Without them, the coordinates would drift by meters. Once again, exactness is not a single fact but a chain of definitions and corrections, all woven around the unyielding standard of time. The interplay of light and time also underpins ranging to other planets. By sending radio pulses to Venus or Mars and measuring the return time, astronomers can fix planetary distances with meter accuracy across millions of kilometers. These measurements refine the ephemerides that predict planetary motions. They also tighten the link between Earth and the solar system as a whole. In this way, the same principle that lets a GPS receiver find your position in a city allows spacecraft to navigate between worlds. All of this rests on the most surprising fact of all, that nature gives us constants to trust. The speed of light is the same everywhere. The oscillations of atoms are identical, no matter where they are measured. These constants allow us to build frames of reference that are not just local conventions, but universal. A second in Paris is the same as a second in Tokyo, and the same as a second on a spacecraft orbiting Saturn, provided we account for relativistic effects. This universality is the foundation of our ability to speak about exact position. From sticks and shadows, we have arrived at atoms and light pulses. The path reveals that the ultimate ruler is not carved wood or etched metal, but the flow of time itself, counted with unimaginable precision. To know where Earth is, we must listen to the beating of atoms and the flashing of light. That realization will carry us deeper into the methods by which time and light weave the net that holds Earth in place. To speak of time as a ruler is to accept that every distance we know is really a story about light in flight. Consider radar pulses sent to the moon. A signal leaves an antenna on Earth, travels through the atmosphere, crosses nearly 400,000 kilometers of empty space, strikes retroreflectors left by the Apollo astronauts, and returns. The round trip takes a little over 2.5 seconds. That span of time, measured by atomic clocks, is turned into a distance with meter accuracy. With decades of repeated measurements, the motion of the moon has been tracked to within millimeters. The lunar orbit is not a guess or a theory. It is a fact written in the ticks of cesium and the constancy of light speed. The same method was extended to planets. Radar ranging to Venus in the 1960s provided one of the first high-precision tests of general relativity, confirming that light curves in the presence of the sun's gravity. Later, ranging to Mars gave distances that refined planetary ephemerides. These ephemerides are the detailed tables predicting where planets will be in the sky at any given time. They are indispensable for spacecraft navigation and for linking Earth's frame to the broader solar system. The accuracy of those tables rests on light travel time, measured in millionths of a second across millions of kilometers. On Earth itself, very long baseline interferometry takes this principle to its extreme. Two radio telescopes separated by continents receive the same signal from a quasar. Because the wavefront arrives at slightly different times, the signals interfere when combined. The tiny difference in arrival time is measured with atomic precision, revealing the baseline distance between the telescopes to within millimeters. By repeating this with many quasars and many stations, scientists measure Earth's rotation, its orientation in space, and even the slow drift of its tectonic plates. Every parameter is tied back to the rhythm of atoms and the constancy of light. Atomic clocks have become more than instruments. They are the foundation of a global infrastructure. The International Bureau of Weights and Measures maintains International Atomic Time, known as TEI, by averaging the signals from hundreds of clocks around the world. Coordinated Universal Time, known as UTC, is then derived by adding leap seconds to keep civil time roughly aligned with Earth's rotation. Without this system, computers, navigation, and communication networks would fall out of sync. The internet, global finance, air traffic, and satellite operations all depend on the steady heartbeat of atoms. The remarkable part is that this heartbeat is still improving. Optical clocks have surpassed cesium in stability by factors of hundreds. They tick so finely that the difference in gravitational potential between your head and your feet can be measured as a change in frequency. In other words, an optical clock on a tall mountain runs slightly faster than one at sea level, and the difference is detectable. This makes clocks not just timekeepers, but sensors of gravity. With networks of optical clocks, geodesy itself can be performed by time alone. The landscape of Earth can be mapped by the way clocks tick faster or slower depending on elevation. Yet, for all this triumph, there are limits. Signals through the atmosphere are bent and delayed by air and ionized plasma. Multipath reflections off buildings corrupt GPS signals in cities. Variations in clock performance accumulate tiny errors. Even the fundamental constants are not beyond question, for theories beyond the standard model of physics predict that the constants themselves might drift over cosmological timescales. Every attempt to define distance and position absolutely leads to deeper questions about what can truly be trusted. Still, the progress is undeniable. A ship once lost at sea now carries a small receiver that can tell its position within meters, and in some cases, within centimeters. Astronomers can locate Earth's center of mass within a few millimeters relative to the solar system barycenter. The cosmos, which once seemed immeasurably vast and imprecise, is now a lattice of times and distances, measured with atomic precision. What began with Harrison's chronometer has become a network of global time transfer systems. Clocks, separated by oceans, are compared with lasers and radio links. Signals are corrected for relativity, which shifts the tick of clocks depending on speed and gravity. Even spacecraft carry atomic clocks, allowing them to navigate independently across the solar system. The vision of position as a simple pair of numbers on a map has blossomed into a symphony of time and light, coordinated across the planet and beyond. But this symphony also shows a subtle truth. The question is no longer only how to measure location, but what location means when everything depends on time. A coordinate is a translation of clock ticks into distance, and of distance into position within a frame. Exactness is not a property of nature alone. It is a construction, built from the agreement that light speed is constant, and that atoms tick reliably. Within that construction, Earth has a place, pinned more tightly with every advance in timekeeping. The deeper we go, the more it becomes clear that time and light are not only tools, but the fabric from which precision itself is woven. To understand Earth's location is to understand how these rulers function at their limits, and what happens when they confront the relativistic nature of the universe. The union of time and light has become so deep that it is hard to imagine measuring without them. Consider again the definition of the meter. No object must be carried to a vault in Paris. No physical artifact is needed. Instead, the measure is encoded in the laws of physics themselves. Every laboratory on Earth, with the right equipment, can recreate the second by counting the oscillations of cesium or strontium atoms. And from that second, they can recreate the meter by letting light travel. This universality has no precedent in history. It makes distance as stable as time, and time as stable as the constants of the universe. From this flows a subtle realization. Every distance is measured twice, once as a journey of light, and once as a count of time. The two are inseparable. To ask how far Earth is from the Sun is to ask how long light takes to cross that span. To ask how high a satellite orbits is to ask how many millionths of a second its signal is delayed. What began as geometry has become chronology. The ruler of space is the clock. This has practical consequences of astonishing scope. Spacecraft navigating to Mars rely on two-way light time. A signal sent from Earth is timed, reflected or echoed by the spacecraft, and timed again on its return. From this single measure, engineers reconstruct orbits across millions of kilometers. The same principle guided the Cassini mission around Saturn and the New Horizons mission past Pluto. Without atomic time, those spacecraft would be lost in the dark. With it, they can be guided through gravitational slingshots and narrow windows of opportunity with meter-scale accuracy. On Earth, the consequences are just as profound. Networks of GPS, Galileo, Beidou, and GLONASS satellites orbit with atomic clocks on board. Each clock is corrected constantly for the distortions of relativity, because time runs differently for satellites in orbit than it does for receivers on the ground. General relativity is not an abstract theory in this context. It is a practical correction written into the code of every navigation signal. Without it, errors would grow to kilometers within a day. With it, positions can be known to within centimeters. The dependence on time is also reshaping science itself. Optical clock experiments now measure gravitational potential differences across hills and valleys, turning the landscape into a field of time variations. The Earth's gravity is mapped not by surveying alone, but by comparing how fast clocks tick in different places. Future geodetic networks may consist not only of satellites and lasers, but of linked optical clocks, each one sensing the curvature of space-time in its own region. Location, gravity, and time will blur into a single concept. But even as these advances unfold, the philosophical question deepens. What does it mean to say exactly where Earth is, when every definition relies on the constancy of light and the oscillations of atoms? If the constants were to drift over eons, would our coordinates drift too? If time itself is relative, then exactness becomes a property of the frame we choose, not of the universe at large. The pursuit of precision leads us not to a final answer, but to a recognition that exactness is always contextual. And yet, within those contexts, The achievements are breathtaking. Earth's orientation is known to milliarc seconds, its center of mass to millimeters, its orbit around the sun to meters. These levels of precision would astonish any earlier age. The partnership of time and light has lifted humanity from crude shadows on the ground to millimeter knowledge of our planet's place in space. The next step is to see how these principles manifest in real time for everyone on the planet. When you pull a phone from your pocket and see a blue dot on a map, you are participating in this grand chain of definitions. Satellites orbit overhead, their clocks corrected by relativity, their signals racing at the speed of light, their positions tied to global frames, anchored by quasars. The blue dot is a distillation of centuries of science, of the marriage of time and light. To follow this story, we must now turn from the foundations to the practical marvel of global navigation satellite systems. They show how the physics of clocks and the constancy of light become everyday tools, locating not only Earth, but every person upon it. When you stand on a city street and open a map on your phone, a glowing dot appears that tells you exactly where you are. It seems ordinary, even mundane, yet behind that dot is one of the most extraordinary technological systems ever built by humankind. The Global Positioning System and its counterparts in other nations are the living expression of centuries of struggle with clocks, light, and coordinates. They embody the principle that time and light together can reveal position with precision once unimaginable. At its heart, GPS is simple in concept. Satellites orbit Earth, each carrying atomic clocks and broadcasting signals that say, in effect, I am here, and this is the time. A receiver on the ground listens to several of these signals at once. By comparing how long each took to arrive, the receiver calculates distances to the satellites. With 4 or more distances, it can solve the puzzle of its own position. This method is called trilateration. It is like measuring your location by knowing how far you are from several lighthouses, except the lighthouses are satellites, moving thousands of kilometers per hour, and the distances are measured not by ropes or chains, but by the flight time of radio waves at the speed of light. The precision of this method rests on 2 pillars. The first is the constancy of light speed. The second is the stability of the satellite's atomic clocks. Each nanosecond of timing corresponds to about 30 centimeters of distance. If the clocks drift by only a few billionths of a second, the position could be wrong by meters. To prevent this, the satellite's clocks are constantly monitored and corrected from the ground. Relativity is also built into the corrections. Because the satellites are high above Earth's surface, in weaker gravity, their clocks tick faster than those on the ground. Because they move quickly in orbit, their clocks tick slower from the perspective of an Earth observer. The 2 effects nearly cancel, but not completely. Without correcting for relativity, the system would be useless within hours. With the corrections, positions are accurate to meters, and with refined methods, to centimeters. This ability to know location in real time has transformed the world. Ships cross oceans without fear of being lost. Aircraft navigate crowded skies with precision. Farmers steer tractors along straight lines across fields to optimize crops. Rideshare services match drivers and passengers with uncanny speed. Even hikers in remote mountains can see exactly where they stand on the map of the world. The blue dot on a screen is a symbol of the fusion of physics, engineering, and everyday life. But GPS is not the only system. The Russian GLONASS, the European Galileo, and the Chinese Beidou all provide their own constellations of satellites. Together they form a global network called GNSS, the Global Navigation Satellite Systems. A modern receiver can listen to signals from all of them at once, increasing accuracy and reliability. This redundancy is vital. Mountains, buildings, and atmospheric disturbances can block or distort signals. By listening to more satellites, the receiver can overcome these obstacles and still calculate a position with confidence. Yet, even with dozens of satellites overhead, precision is never perfect. The signals must pass through the ionosphere, a layer of charged particles that delays radio waves, and through the troposphere, where water vapor bends them unpredictably. Multipath reflections from buildings can make signals appear to arrive later than they truly do. Engineers apply sophisticated corrections and models to minimize these errors, but they remain a source of uncertainty. Even the best receiver must accept a small margin of error. Exactness, once again, depends on context. Still, the achievement is staggering. A sailor once relied on sextants and stars to know latitude within a few kilometers. Today, a phone in the palm of your hand can know its position within a few meters in seconds. With advanced techniques such as real-time kinematic positioning and precise point positioning, accuracy can reach centimeters. Surveyors, geologists, and engineers routinely rely on this. They measure tectonic shifts, monitor dams, and guide autonomous machines, all using signals whispered from orbiting satellites. This is the great paradox of GPS. It is at once ordinary and profound. It is used casually to find a coffee shop, yet it depends on atomic physics, relativity, and global cooperation. It makes the world feel small and navigable, yet it reveals Earth's motion in space with startling clarity. It is the culmination of the long journey from Eratosthenes' shadows to atomic clocks, now placed in orbit to guide everyone, everywhere, all the time. And it raises a deeper question. If every receiver can know its position relative to satellites, how do we know the position of Earth itself relative to the cosmos? The satellites are tied to Earth's frame, which itself is in motion. To place Earth in its true context requires recognizing that its position is not fixed. It wobbles, shifts, and drifts, like a top unsteadily spinning on a table. And so, to push beyond the blue dot, we must confront the dance of Earth itself. The satellites glide above us in carefully chosen orbits, circling Earth twice each day at an altitude of about 20,000 kilometers. From such heights, each satellite's broadcast covers nearly half the globe. The signals fall like invisible rain, available to anyone with a receiver. There is no distinction of class, nation, or wealth in their basic operation. A fisherman in the Pacific and a driver in Paris both share the same access to timing pulses from orbit, and both translate those pulses into knowledge of where they are. But while the principle of trilateration is straightforward, the practice is tangled in details. The first challenge is the atmosphere. The ionosphere, filled with charged particles, slows the passage of radio waves. The amount of delay depends on the density of electrons along the path, which changes with solar activity, time of day, and latitude. To overcome this, satellites broadcast on more than one frequency. By comparing the delays at two frequencies, the receiver can estimate the ionospheric effect and remove it. The troposphere poses a subtler challenge. Water vapor bends the signals in ways that are harder to model. Meteorological data and statistical models are used to apply corrections, but the uncertainty never vanishes entirely. The second challenge is relativity itself. The satellite's clocks tick faster because they are higher in Earth's gravitational field, and they tick slower because of their orbital speed. The net effect is that their clocks run about 38 microseconds faster per day than clocks on the ground. That might seem tiny, but at the speed of light, it corresponds to more than 10 kilometers of error every 24 hours. Engineers account for this by pre-adjusting the frequency of the satellite's clocks on the ground before launch and by applying continuous corrections in orbit. Relativity is thus not a footnote, but a constant companion, embedded in the very code that carries the signals. A third challenge lies in the orbits themselves. The satellites do not follow perfect paths. The pull of the moon and sun, the drag of Earth's atmosphere at high altitudes, and even the pressure of sunlight all perturb their motion. Ground stations track the satellites continuously, updating their orbital data. These updates are uploaded to the satellites and broadcast as part of the navigation message. Your receiver is not only listening to time signals, it is also absorbing the orbital ephemerides that allow it to reconstruct where each satellite was at the moment of transmission. Without this information, trilateration would be impossible. Despite these obstacles, GPS and its cousins achieve remarkable precision. For everyday use, an accuracy of a few meters is typical. With differential techniques, Where corrections from fixed base stations are applied, accuracy improves to decimeters or centimeters. Precise point positioning takes the method further, using global correction data to achieve centimeter accuracy without the need for a local base. Surveyors routinely map terrain with this method. Earth scientists track the drift of tectonic plates. Engineers monitor the stability of bridges and dams. The system has become not just a tool of navigation, but a backbone of science and engineering, and all of it depends on time. Each satellite carries atomic clocks, originally cesium or rubidium, now sometimes augmented by hydrogen masers. Their frequencies are calibrated to better than 1 part in a trillion. On the ground, master control stations compare the satellite's clocks with reference clocks tied to international atomic time. Any drift is corrected by adjusting the broadcast parameters. The network of satellites thus acts as a constellation of flying clocks, their signals knitted into a single global time. The miracle is that this timekeeping is freely available to anyone who listens. This universal access hides its fragility. A strong enough burst of radio interference can overwhelm the weak satellite signals, which arrive at the ground with less power than a light bulb shining hundreds of kilometers away. Solar storms can flood the ionosphere with particles, disrupting the signals unpredictably. Military forces develop jammers and spoofers that can deceive receivers. The very system that guides aircraft and ambulances is vulnerable to the thinness of its own signals. Engineers work constantly on defenses, from encrypted signals to regional augmentation systems. Still, the reliance on GNSS is a delicate balance between marvel and vulnerability. What makes the achievement even more striking is that it binds Earth to space in real time. A position on the ground is not fixed locally but defined by orbital dynamics, atomic physics, and the constancy of light speed. When you see your location on a screen, you are not standing on a static Earth. You are standing within a lattice that stretches from orbit to quasar, from atom to universe. The blue dot is the visible surface of a system that reaches across scales of space and time. And yet, this lattice is not rigid. Earth itself is moving, wobbling, and deforming under the pull of the moon and the sunday. To say exactly where we are requires accounting for those motions. The satellites tie us to Earth's center of mass, but that center itself is restless. To understand the true position of Earth, we must step beyond the satellites and face the wobble of the planet itself. The miracle of global navigation satellite systems is that they have dissolved the distance between the grand and the ordinary. They serve both a scientist probing tectonic drift and a pedestrian finding a cafe. Yet the same physics underlies both. The signals that guide an aircraft across oceans are the same as those that guide a child's toy drone in a backyard. This democratization of precision is unprecedented. The great enterprises of geodesy and astronomy have spilled into the pockets of billions of people. But precision is always a negotiation with error. Multipath reflections in cities create the familiar jump of the blue dot from street to street. Signals bending in the ionosphere can misplace a receiver by meters if not corrected. Even the arrangement of satellites overhead affects accuracy. When satellites are clustered in one part of the sky, the geometry is poor and errors grow. When they are spread across the heavens, the solution sharpens. Receivers constantly compute this geometry, called dilution of precision, to estimate their own uncertainty. Behind the apparent simplicity of a coordinate lies a rolling calculation of probabilities. Advanced methods push beyond these limitations. Real-time kinematic positioning uses a fixed base station with known coordinates to send corrections to mobile receivers. By comparing the phase of the satellite signals rather than just their timing, it achieves centimeter accuracy. Precise point positioning extends the principle globally, using correction data from international networks. These techniques are routine in surveying, construction, and agriculture, where straight lines and exact boundaries matter. They are also essential in science, where millimeter motions of the crust reveal the strain that builds earthquakes and the rise and fall of continents under the weight of melting ice. The reach of GNSS extends beyond Earth itself. Satellites in orbit around Earth use GPS to determine their positions. Spacecraft near the Moon and even Mars have experimented with using navigation signals as far as they can reach. The idea of an interplanetary navigation system is no longer science fiction, but an engineering frontier. Already, the same principles that allow your phone to find a cafe could one day allow a rover on Mars to know its place among the canyons. Yet, beneath all this triumph lies the restless motion of Earth. The satellites are tied to Earth's center of mass, but that center does not stand still. Earth is not a rigid body, but a dynamic system. The crust flexes under the pull of the Moon, and the Sunday, oceans slosh, air shifts, ice melts, and the entire distribution of mass changes from day to day. These changes move Earth's center by millimeters to centimeters, altering the very frame that GPS is tied to. A coordinate is never absolute, but always relative to a shifting whole. This truth shows in the data. Long-term GNSS measurements reveal the Chandler wobble, a subtle wandering of Earth's poles, with a period of about 430 days. They show precession and nutation, the slow dance of Earth's axis under solar and lunar torques. They show polar motion, as ice and water shift masses across the globe. Each of these effects is measured because GNSS is more than navigation. It is a planetary observatory, a global stethoscope, listening to the beating of Earth's mass and rotation. Thus, the blue dot on a map is the endpoint of a cosmic chain. It ties a pedestrian's footsteps to atomic clocks in orbit, to frames of reference anchored by quasars, and to the restless mass of Earth itself. It shows not only where you are, but how that place shifts as Earth wobbles, spins, and drifts. To understand exactly where Earth is, we must now follow these wobbles. We must confront the motions that never cease, the subtle dances that displace even the most careful frames. And so the story passes from satellites to the spinning planet beneath them. To move from precision to exactness, we must understand the wobble of Earth itself. The Earth does not sit still. It spins, it tilts, and it wobbles in ways both subtle and profound. To an observer standing on the ground, the planet may feel solid and unmoving, but when measured with atomic clocks, lasers, and radio telescopes, Earth reveals itself as a restless body. To know exactly where Earth is means not only measuring coordinates, but accounting for motions that shift those coordinates from moment to moment. The planet is atop in slow motion, its axis leaning, circling, and trembling under the pull of the heavens. The largest of these motions is called precession. Over thousands of years, the axis of Earth slowly traces a wide circle in the sky. Today, the North Pole points toward Polaris, the pole star. But in the time of the ancient Egyptians, it pointed toward a different star, Thuban, and in another 12,000 years it will point toward Vega. This slow sweep, with a period of about 26,000 years, is caused by the gravitational pull of the Sun and Moon on Earth's equatorial bulge. Just as a spinning top wobbles under gravity, Earth's tilted axis wobbles under celestial torques. Precession shifts the orientation of the planet in space, changing the background against which coordinates are measured. Layered upon this long cycle is a smaller trembling called nutation. The pull of the Moon, which varies as the lunar orbit tilts and stretches, causes Earth's axis to nod back and forth, with a rhythm of about 18.5 years, along with smaller oscillations at other periods. Nutation is subtle, a matter of arcseconds in angle, but for precision astronomy and navigation, it cannot be ignored. Every quiver of the axis alters the apparent positions of stars, the timing of satellite signals, and the transformation between terrestrial and celestial frames. Closer to daily life are the tides. We usually think of tides as the rise and fall of ocean water, but Earth itself also flexes. The solid crust is pulled upward and downward by the gravity of the Moon and the Sun, deforming by tens of centimeters twice each day. The oceans amplify the effect, moving masses of water that in turn shift Earth's center of mass. These tidal deformations mean that the very shape of the planet changes continually. A mountain peak or a city street is not in the same place at noon as it was at midnight, because the ground itself has risen and fallen with the tide. These motions might seem academic, but their consequences are real. A GPS receiver in Japan detects Earth's wobble as the tectonic plate beneath it drifts. The tides shift its height, and polar motion nudges its coordinates. A laser ranging station firing pulses at satellites must account for the tiny shifts in the ground between shots. Astronomers linking telescopes across oceans must calculate the wobble of Earth's axis to align signals from quasars. In every case, ignoring the wobble would destroy precision. Accounting for it turns chaos into clarity. The Chandler wobble adds yet another layer. This is a free oscillation of Earth's rotation axis, discovered in the late 19th century by the American astronomer Seth Chandler. It has a period of about 430 days and an amplitude of a few meters at the surface. The cause is a mix of Earth's elastic structure, ocean currents, and atmospheric motion. Like a spinning top that does not balance perfectly, Earth's axis drifts irregularly. Tracking this wobble requires global networks of GPS stations and very long baseline interferometry. Without it, the reference frames that tie Earth to space would slip by centimeters each year. Each of these wobbles, precession, nutation, tidal flexing, and Chandler oscillation adds to the restless character of Earth. Together they paint a picture of a planet always in motion, never fixed. The idea of an exact coordinate becomes fragile. It can only mean a position within a defined frame, at a defined time, corrected for all the known wobbles and shifts. The more precise the measurement, the more corrections are required. And yet, this very restlessness is a gift. By measuring Earth's wobbles, scientists learn about its interior, its oceans, and its atmosphere. The way the axis nods reveals the distribution of mass. The way the crust flexes reveals its elasticity. The way the Chandler wobble drifts reveals the flows of air and water. The pursuit of exact position becomes a window into Earth's physics. What began as a question of navigation expands into a science of the whole planet. To understand Earth's wobble fully, we must look not only at its surface, but at its center. The location of the center of mass, the geocenter, shifts as air and water move. Pinning Earth's position requires tying that center to the broader solar system. And so, from wobble, the path leads outward, to Earth's place among the planets, and to the barycenter, around which the entire solar system turns. The realization that Earth wobbles in so many ways might seem unsettling. If the ground itself moves, how can we ever claim to know exactly where we are? The answer is that we measure the wobble itself with extraordinary care, turning uncertainty into knowledge. Over the past century, entire fields of science have been built upon tracking Earth's shifting axis and center of mass, using methods that combine the most delicate instruments with the largest scales imaginable. One of the most elegant techniques is satellite laser ranging. The principle is simple. Fire a laser pulse from Earth to a satellite equipped with retroreflectors. Then measure the time it takes for the pulse to return. Because light travels at a fixed speed, the round-trip time gives the distance to the satellite with millimeter accuracy. Repeat the process millions of times, and the satellite's orbit can be reconstructed with exquisite detail. But the orbit itself is a reflection of Earth's gravity and motion. By watching the satellite, we are in fact watching Earth. Shifts in the planet's mass distribution tug on the orbit. Wobbles in the axis reveal themselves as small drifts. What seems like measuring a spacecraft is actually measuring our own restless planet. Another powerful method is very long baseline interferometry. By linking radio telescopes across continents, astronomers can measure the arrival times of signals from distant quasars to fractions of a nanosecond. These differences encode the orientation of Earth's rotation axis and the length of the day. Because the quasars are so distant, their positions are effectively fixed. They provide a stable backdrop against which Earth's spin can be tracked. Each observation refines our knowledge of precession, nutation, and polar motion. The technique is so sensitive that it reveals not only the steady wobble of Earth but also fluctuations caused by winds and currents, shifting atmospheric mass. Then there is Doppler orbitography, a method that uses the Doppler shift of signals from satellites to determine positions. As a satellite passes overhead, its signal is stretched and compressed by its motion. By measuring this shift, ground stations can calculate the satellite's orbit. Systems like DORIS developed in France, use this principle to provide global measurements of Earth's shape and motion. Each orbit is a delicate dance influenced by Earth's wobbles, and by analyzing them, the planet's shifting center of mass is revealed. Together, these techniques feed into the International Earth Rotation and Reference System Service, an organization that maintains the official parameters describing Earth's wobble. Each day, scientists update values for precession, nutation, polar motion, and the length of day. These parameters are used to transform between the terrestrial frame tied to Earth's surface and the celestial frame tied to quasars. Without these corrections, navigation and astronomy would quickly drift into chaos. Telescopes would miss their targets, satellites would misplace themselves, and even GPS would degrade. With them, the lattice of precision holds together. The data reveal a planet alive with motion. The length of day varies by milliseconds as winds roar in the atmosphere and currents surge in the oceans. The poles wander unpredictably by meters over decades, their path traced by the Chandler wobble. Seasonal changes in snow and ice shift the distribution of mass, nudging the axis subtly. Earthquakes release stress and alter the spin fractionally. Each effect is tiny, but together they form a restless rhythm. To track them requires global cooperation, with observatories, satellites, and analysis centers sharing data continuously. What emerges from this effort is not only knowledge of Earth's wobble, but also insight into its interior. The way the planet responds to tidal forces tells us about its mantle's elasticity and the liquid nature of its core. The way the Chandler wobble drifts provides clues about the coupling between the core and mantle. The subtle variations in nutation reveal the influence of atmospheric and oceanic angular momentum. In this sense, measuring Earth's wobble is like listening to the planet's heartbeat. Each tremor carries information about its hidden structure and dynamics. This pursuit of wobble has profound implications for practical life. Sea level rise cannot be measured without knowing whether the land itself is rising or sinking. Satellite orbits cannot be predicted without accounting for the shifting geocenter. Astronomical observations cannot be aligned without correcting for precession and nutation. The dream of pinpointing Earth's location with millimeter precision rests entirely on understanding and modeling these wobbles. And yet, even with all the corrections, the question of exactness remains elusive. Earth's wobble is not perfectly predictable. Polar motion wanders chaotically at times. The Chandler wobble varies in amplitude and phase. Sudden changes occur when earthquakes or shifts in circulation redistribute mass abruptly. What scientists provide is not a single fixed number, but a constantly updated model. Exactness exists only as a moving target, recalculated with each new set of observations. This fragility does not undermine the achievement. On the contrary, it reveals the depth of our reach. Humanity can now measure the planet's axis drifting by meters over decades, its crust flexing by centimeters under tides, and its day lengthening by milliseconds as the moon pulls it. These are not abstract numbers. They are the motions of the ground beneath our feet, captured and understood through the marriage of light, time, and observation. To truly fix Earth's place, however, requires extending beyond its own restless surface. The center of mass must be tied to the solar system as a whole. Earth's position only becomes absolute when measured against the barycenter, the common center of gravity of all the planets, and the Sunday. The wobble of Earth prepares us for this next step, where our planet's place is pinned not only by its own axis, but by the gravitational ballet of the solar system. The picture that emerges from all these corrections is not of a static world, but of a planet constantly shifting under invisible hands. Earth is not a rigid body frozen in space. It is elastic, fluid, and alive with motion. The sun and moon pull at it daily, lifting oceans and flexing the crust. Winds sweep across its atmosphere, redistributing angular momentum. Ice melts and water flows, tugging the geocenter by millimeters. Deep inside, the liquid core couples imperfectly to the mantle, adding subtle irregularities to the spin. To know exactly where Earth is means following all these motions in real time, like tracing the path of a dancer whose steps never repeat. The corrections themselves form a remarkable hierarchy. Precession describes the long sweep of the axis over 26,000 years. Nutation adds smaller, periodic nods of years to decades. The Chandler wobble overlays a free oscillation of more than a year. Polar motion drifts chaotically by meters over decades. Solid Earth tides flex the crust by centimeters twice a day. Ocean tides redistribute billions of tons of water, shifting the geocenter. Atmospheric tides, though faint, leave their trace as well. Each layer must be measured, modeled, and subtracted to reveal Earth's true orientation and position at any moment. The task might sound overwhelming, yet it has become routine. Every day, observatories around the world measure these motions. Data streams flow into international centers where models are updated and distributed. Astronomers who aim a telescope at a quasar, engineers who guide a satellite, and surveyors who map a city all rely on these updates. Without them, their work would drift into error. The entire system of global positioning and celestial navigation rests on the quiet, continuous labor of modeling Earth's wobble. And this labor has given profound scientific rewards. By studying precession, we confirm the torque of the sun and moon on Earth's bulge. By studying nutation, we probe the liquid core's coupling to the mantle. By tracking polar motion, we learn how climate shifts mass across the globe. By monitoring the Chandler wobble, we uncover interactions between the atmosphere, oceans, and Earth's elastic structure. Each wobble is not just a nuisance to be corrected, but a window into Earth's dynamics. The pursuit of exactness turns into a deeper understanding of the planet itself. Still, the philosophical question remains. When we say Earth's position is known to millimeters, what exactly do we mean? Do we mean the position of the crust at a given observatory, knowing it flexes with tides and drifts with plates? Do we mean the geocenter, knowing it shifts with water and air? Do we mean the axis orientation relative to quasars, knowing it precesses and nutates? Each answer is correct within its frame, yet none is eternal. Exactness exists only as agreement, renewed daily by observation and modeling. This realization prepares us for the next step outward, for even when we have tamed Earth's wobble, the planet is still not pinned in any final sense. It circles the sun, and the sun itself does not sit at the center of the solar system. Instead, all the planets and the sun orbit their common barycenter, a point that can lie inside or outside the sun's surface, depending on the positions of Jupiter and Saturn. To locate Earth absolutely requires locating it relative to this barycenter. The wobble we measure on Earth is only one layer of a larger dance, choreographed by the gravity of the entire solar system. So the story turns outward once more, from the subtle tides that lift the crust by centimeters, to the slow sweep of precession shifting the pole star, to the restless wandering of polar motion. We see Earth as a body in motion. To locate it precisely, we must extend beyond the planet and tie it to the solar system itself. The next chapter will trace how this is done, how Earth's orbit and its relation to the barycenter define its position in the celestial ballet. Only then can we begin to speak of Earth's exact place among the planets. To place Earth within the universe, it is not enough to say where it is on its own surface or even relative to the distant quasars. For all our precision, we are still carried along by a larger motion. Earth circles the sun, and the sun itself circles a point that does not lie at its center. To speak of Earth's true location in the solar system requires us to face the idea of the barycenter, the balance point of gravity around which the entire system turns. Imagine holding a hammer by its handle and spinning it. The hammer does not rotate around the exact center of its head, but around a point in space between the heavy head and the lighter handle. The solar system behaves in much the same way. The sun is massive, but it does not sit fixed at the center. Instead, Jupiter, Saturn, and the other planets tug on it, pulling the balance point outward. Sometimes the barycenter lies within the body of the Sunday. At other times it lies just outside, in empty space. The sun moves in a small orbit around this point, and Earth follows along, circling a moving star. This complicates the notion of location. If we say Earth is one astronomical unit from the sun, What do we really mean? Do we mean its distance from the Sun's center, which itself is wobbling around the barycenter? Or do we mean its distance from the barycenter, which defines the true gravitational center of the solar system? Astronomers resolve this by defining heliocentric and barycentric coordinates, and by calculating precise ephemerides that predict positions in either frame. Each definition serves a purpose, and each must be chosen carefully, depending on context. To compute these positions, astronomers rely on planetary ephemerides' vast tables of coordinates generated by integrating the equations of motion for all planets, moons, and major asteroids under mutual gravitational pull. The most famous are the DE series produced by the Jet Propulsion Laboratory and their European counterparts such as INPOP. These ephemerides are not mere predictions. They are constantly refined by data from spacecraft tracking, radar ranging, and optical observations. Each new mission that flies past Mars or Saturn sharpens the model. Each radar echo from Venus pins the distance more tightly. The solar system becomes a web of measurements, all feeding back into the question of where Earth is at any given moment. The need for such refinement is clear. Jupiter alone, with its immense mass, pulls strongly enough on the Sun to drag the barycenter well outside the solar surface. Saturn adds its own influence, tilting and shifting the balance point. Even the smaller planets contribute, though more subtly. As they orbit, the barycenter dances within and around the Sun, tracing loops that change from year to year. Earth's orbit around the Sun is therefore an orbit around a moving target. The precise coordinates of Earth depend not only on its own motion, but on the gravitational choreography of the entire system. For centuries, astronomers could only approximate these motions. Kepler described the orbits as ellipses. Newton explained them with universal gravitation. But it was only with radar and spacecraft telemetry that positions became known to meters instead of millions of kilometers. When signals bounced off Venus in the 1960s, they provided distances accurate enough to reveal flaws in earlier ephemerides. Later, spacecraft like Cassini, Messenger, and Juno carried transponders that allowed two-way light-time measurements across hundreds of millions of kilometers. These data pulled the barycentric model of the solar system into sharper focus, reducing uncertainties in Earth's position to tens of meters. The philosophical weight of this is immense. We are used to thinking of the Sun as fixed, the anchor around which Earth revolves. But in truth, the Sun is a participant in the dance, pulled and shifted by its planets. Earth's orbit is not a simple ellipse, but a path around a moving center, guided by the combined gravity of the solar system. To know exactly where Earth is requires knowing exactly where Jupiter is, where Saturn is, and even where the smaller worlds wander. Earth's position cannot be isolated. It is part of a system, inseparable from the motions of its companions. This interdependence has practical consequences. Spacecraft navigation depends on ephemerides accurate enough to predict where planets will be when a spacecraft arrives years later. A small error in Earth's position ripples into errors in Mars's predicted position, and a mission could miss its target by thousands of kilometers. For this reason, planetary ephemerides are refined constantly, blending data from many sources. When New Horizons flew past Pluto, its tracking data improved not only Pluto's orbit but Earth's, because all are linked in the same system. And so, the question of Earth's location turns outward. It is no longer only about longitude and latitude, or even about precession and wobble. It is about how the entire solar system moves, how the balance of gravity defines a shifting barycenter, and how Earth is carried in that cosmic dance. To speak of exactness now means choosing a frame heliocentric, barycentric, or another, and anchoring Earth's coordinates within it. This realization opens the door to a broader challenge. To place Earth beyond the solar system, we must tie it not just to the barycenter, but to something more stable, something beyond the influence of planetary motions. The next step lies with the stars themselves, or rather, with the quasars that form our ultimate inertial frame. But before we reach them, we must linger longer in the solar system, exploring the details of barycenters, orbits, and the precision tools that make their measurement possible. To know Earth's orbit with precision, we must measure it not only from within, but also against the planets and the Sunday. The most direct tool is radar ranging. In the 1960s, powerful transmitters beamed pulses toward Venus and Mercury, waiting for their faint echoes to return. By counting the round-trip time of the signals, astronomers could measure planetary distances to within hundreds of meters across tens of millions of kilometers. This leap in accuracy transformed celestial mechanics. The orbits of Earth and Venus were no longer abstract ellipses traced on paper, but distances tested by light in flight. Radar ranging gave the first high-precision tests of general relativity, showing that signals passing near the Sun were delayed more than Newtonian gravity would predict. It also refined the astronomical unit, once defined as Earth's average distance from the Sunday. The AU became measurable in terms of seconds of light travel, tying it directly to the speed of light. With radar, Earth's orbit was no longer inferred. It was measured, yet radar has limits. Beyond Mars, distances grow too vast and reflections too weak. For the outer planets, spacecraft tracking provides the answer. When a probe like Voyager, Cassini, or Juno carries a radio transponder, engineers on Earth send a signal, the spacecraft returns it, and the round-trip time is measured with nanosecond precision. The Doppler shift of the returning signal reveals the spacecraft's speed to fractions of a millimeter per second. Together, these data fix the spacecraft's trajectory, and by extension, the positions of the planets that influence it. Every flyby refines the ephemerides not only of the target planet but of Earth, because the system must be solved as a whole. The Cassini mission around Saturn became one of the great refiners of planetary ephemerides. Its long series of radio tracking data tightened the orbit of Saturn and the barycentric model of the solar system. Messenger at Mercury did the same, as did Mars orbiters. Even spacecraft that missed their original goals, like Mariner missions that flew past Venus, left behind data that fed into the larger web. Each mission was both an exploration and a measurement, tying Earth more tightly to the barycenter. The ephemerides themselves, such as the DE series from the Jet Propulsion Laboratory, are immense numerical integrations. They begin with Newton's and Einstein's laws of motion and gravity, add corrections for relativistic effects, and account for thousands of gravitational interactions. The equations are solved step by step across centuries, adjusted continuously by new data. Each time a radar pulse reflects from Venus or a spacecraft arcs past Mars, the parameters are tweaked. The resulting tables can predict the position of Earth, Mars, or Jupiter to meters over decades. Without them, navigation of spacecraft would be blind. With them, probes can thread narrow corridors past moons and into orbits. The refinement never stops. Even small asteroids, once ignored, are now included because their tiny gravitational pulls accumulate over time. Mass redistributions within planets alter their gravitational harmonics, which must be modeled. Relativistic corrections for light travel and time dilation are added with exquisite care. The process resembles tuning a vast symphony, where each note is adjusted until the harmonies align. The score is Earth's position within the solar system, and the instruments are light, time, and gravity. This effort reveals just how interconnected the solar system is. Earth's orbit cannot be solved in isolation. It depends on the mass of Jupiter, the tilt of Saturn, the eccentricity of Mars, and even the density of the asteroid belt. A small error in one propagates to all. To say where Earth is, you must say where the planets are. To say where the planets are, you must solve for Earth. The system is holistic. Location is not a property of a single world, but of the entire dance. The practical consequences are enormous. When engineers plot the course of a spacecraft, they rely on ephemerides to know where Earth will be years later, when the craft swings by for a gravity assist. A 1-kilometer error in Earth's position could mean a miss of thousands of kilometers at Jupiter. The precision of missions like Voyager, Cassini, and New Horizons is testimony to the refinement of ephemerides. The spacecraft arrived on target because Earth's place in the solar system was known to within meters. This precision also feeds into our understanding of time itself. The motions of Earth around the barycenter affect the timing of signals from pulsars and quasars. Astronomers must correct for Earth's orbital motion to detect tiny changes in those signals. In this way, knowledge of Earth's orbit ties into cosmology, gravitational wave astronomy, and the search for planets around distant stars. The humble question of where Earth is echoes outward into the universe. And yet, just as with terrestrial wobble, exactness has limits. Ephemerides are models, constantly refined but never final. Uncertainties remain, especially for the outer planets where data are sparse. Even Jupiter, so influential, carries small unknowns that ripple into Earth's predicted position. To speak of exactness is to speak of a probability, a cloud of possible positions that narrows with each new measurement, but never vanishes entirely. Still, the achievement is extraordinary. From shadows on the ground to radar echoes of Venus, from ancient sextants to spacecraft streaking past Saturn, humanity has transformed Earth's orbit from myth to meter. The barycenter, once an abstract point, has become a measurable reality, and Earth, once imagined at the center of all things, is now known as a participant in a gravitational dance whose precision we can calculate and whose rhythm we can follow. But if the solar system is the stage, we must still ask, what is the backdrop? To place Earth beyond the shifting barycenter, we must fix it against something more stable, something not swayed by planetary orbits. For this, astronomers turn their gaze outward, anchoring Earth's place to the distant light of quasars. To speak of Earth's orbit is to speak of motion on every scale. The planet circles the Sun in 1 year. The Sun circles the barycenter in loops, shaped by Jupiter and Saturn, and the entire solar system sweeps through the galaxy at hundreds of kilometers per second. Each layer complicates the notion of exact location, and yet, through the tools of modern astronomy, these motions can be measured with breathtaking precision. The barycenter itself is not a fixed point in space. It shifts continually as the planets move. When Jupiter and Saturn align on the same side of the Sun, their combined pull drags the barycenter well outside the solar surface. When they are on opposite sides, their pulls partly cancel, and the barycenter retreats closer to the Sun's center. The loops traced by the barycenter over years resemble a celestial dance, a weaving of gravity that the Sun and all the planets must follow. Earth's orbit, in this view, is not an ellipse around the Sun, but a wave-like path around a moving target. This subtle truth shows in the data. Planetary ephemerides reveal that Earth's heliocentric coordinates and its barycentric coordinates differ by thousands of kilometers, depending on the epoch. For practical life on Earth, such differences do not matter, but for spacecraft navigation, pulsar timing, and cosmology, they are crucial. When astronomers correct the arrival times of signals from distant pulsars, they must subtract the motion of Earth around the barycenter, not just around the Sunday. Only then can they hear the faint ripples of gravitational waves or detect the presence of an exoplanet tugging on its host star. The refinement of these models is ongoing. Each new mission improves them. When Cassini orbited Saturn, it not only mapped that planet's moons, but also pinned the mass of Saturn more tightly, improving the barycentric solution. Messenger at Mercury did the same, sharpening knowledge of Earth's orbit by constraining the innermost planet's pull. Even New Horizons, racing past Pluto, contributed data that rippled back into the ephemerides, improving the accuracy of Earth's position relative to the barycenter. Each spacecraft is a surveyor, measuring Earth's place as surely as it measures its own. In this way, Earth's location is inseparable from exploration. The probes that chart the solar system also chart our own orbit. The distances that guided their journeys are the same distances that define where Earth is today. To know exactly where a spacecraft will be at Jupiter is to know exactly where Earth was when it left. Navigation and astronomy fuse into a single enterprise, anchored by the constancy of light and the precision of clocks. Yet, as always, exactness has its limits. Even with modern ephemerides, uncertainties remain. Small asteroids exert cumulative pulls. The solar mass distribution changes as the Sun's activity waxes and wanes. Relativistic corrections must be applied with care, and new physics might one day shift the models again. The confidence intervals shrink, but never vanish. Earth's barycentric position can be given to meters, but beyond that lies the haze of uncertainty, the reminder that no measurement is absolute. Still, the achievement is profound. Humanity has moved from myths of a fixed, sun-centered cosmos to a measured understanding of barycenters and orbital mechanics. We know that the sun itself is not fixed, that Earth does not circle it in isolation, and that the true center lies in a moving point defined by all the planets together. To locate Earth, we must locate the entire solar system, and in doing so, we discover the deeper truth that we are part of a collective motion, inseparable from the other worlds. But there is one more step. The barycenter itself drifts through the galaxy, carried in orbit around the Milky Way. To define Earth's place with stability, we need a backdrop beyond planetary motion. We need anchors that do not drift with the solar system, that shine from so far away their apparent positions are fixed for human history. Such anchors exist in the form of quasars, brilliant beacons powered by black holes billions of light years away. By tying Earth's coordinates to these distant lights, astronomers create the ultimate inertial frame, against which the motion of the solar system itself can be measured. And so, the next chapter turns outward again, from the solar system barycenter to the stars that do not move. There, Earth will be placed in a frame that transcends its local dance, tied to the deepest structures of the universe. For millennia, the fixed stars were humanity's most trusted guides. Sailors steered by Polaris, architects aligned temples to Orion, and calendars marked the seasons by the return of familiar constellations. To the naked eye, the stars seemed immutable, a backdrop against which planets wandered and Earth spun. But the stars themselves move, each one an orbiting member of the Milky Way. Their proper motions, though imperceptible over a human lifetime, become measurable with precision instruments. For the most exacting purposes, even stars are not fixed enough. Astronomers needed anchors that would not drift, points so distant that their motion across the sky would be negligible for tens of thousands of years. The solution came not from ordinary stars but from quasars, the luminous hearts of galaxies, powered by supermassive black holes. Quasars lie billions of light years away, their radio emissions piercing the universe with remarkable stability. Their distances are so vast that any actual motion they possess translates into shifts far smaller than 1,000th of an arcsecond, as seen from Earth. In practice, they are as fixed as anything the cosmos provides. By observing quasars with very long baseline interferometry, astronomers established a grid of reference points across the sky. Each quasar became a pin in a cosmic map, its position determined by comparing signals received at radio telescopes, separated by continents. Because the radio waves arrive at slightly different times at each station, the differences can be measured to fractions of a nanosecond. From this, the positions of the quasars are fixed with micro-arcsecond precision. The International Celestial Reference Frame, or ICRF, was born. The ICRF is more than a catalogue. It is the inertial frame of modern astronomy. When we say Earth is tilted by about 23.5 degrees, that tilt is measured relative to the ICRF. When spacecraft navigate through the solar system, their positions are calculated relative to the ICRF. When pulsars are timed to search for gravitational waves, the corrections for Earth's motion are made against the ICRF. It is the backdrop against which all celestial mechanics are pinned. What makes this achievement remarkable is the scale. The quasars are not close neighbors, but ancient lighthouses, their light and radio waves traveling for billions of years before reaching us. Some shine from the era when galaxies were young, their black holes devouring matter at furious rates. Yet from such extreme distances, their positions are steady enough to guide spacecraft and define Earth's place to millimeter precision. In using quasars, humanity has anchored itself not to the shifting stars of the Milky Way, but to the deep structure of the universe. This anchoring is not absolute, for even quasars have their subtleties. Some exhibit small structural changes in their radio jets, which can shift their apparent positions. Others flare and fade, complicating measurements. But by averaging across many quasars, and by choosing those with the most stable emissions, astronomers build a reference frame as close to immutable as physics allows. The ICRF now contains thousands of quasars, forming a dense net of positions that covers the entire sky. The implications are profound. With the ICRF in place, Earth's orientation and orbit can be measured not only relative to the solar system barycenter, but relative to the distant universe. The wobbles of precession and nutation, the drift of polar motion, and the loops of the barycenter are all described against a backdrop that does not move. This transforms the pursuit of exactness. Earth's location can now be given not only in relation to the sun or planets, but in coordinates that remain fixed for cosmic timescales. And yet, this achievement also deepens the philosophical question. If we are anchored to quasars, then we are anchored to points whose light began its journey billions of years ago. We see them not as they are now, but as they were when the universe was young. Our frame of reference is built on ancient light, a frozen record of distant epochs. To say exactly where Earth is relative to the ICRF is to tie ourselves to a past that may no longer exist, but for all practical purposes, this ancient scaffolding is the most stable we will ever know. The shift from stars to quasars marks a turning point in human measurement. It is the moment when we stopped using the galaxy as our backdrop and reached into the universe itself. From here, Earth's position is no longer merely planetary or solar. It is cosmic, defined by the flickering hearts of galaxies billions of light years away. Very long baseline interferometry, known as VLBI, is the workhorse of the celestial reference frame. The idea is deceptively simple. Take two or more radio telescopes, separated by thousands of kilometers, point them at the same quasar, and record the incoming signals with exquisite timing. Because the telescopes are far apart, the quasar's wavefront reaches them at slightly different times. By comparing the recordings afterward, the difference in arrival times can be measured to trillionths of a second. This difference translates directly into distance between the telescopes and into the direction of the quasar. In practice, VLBI is a triumph of coordination. The telescopes must keep time with atomic clocks so stable that their drift is less than a nanosecond per day. The recordings, once captured, are shipped or transmitted to a central correlator, where powerful computers align them to within fractions of a wavelength. The result is an angular resolution finer than any optical telescope can achieve, capable of pinpointing quasar positions to microarcseconds. To put that scale in perspective, 1 microarcsecond is the angle subtended by a coin on the surface of the Moon. By repeating this process across hundreds of quasars, astronomers construct a celestial grid that is both vast and precise. Each quasar's position is catalogued relative to all the others, creating a network of reference points spread across the entire sky. This is the International Celestial Reference Frame. Its first version, released in the 1990s, relied on a few hundred quasars. The current versions use thousands, with positions refined over decades of repeated observation. The frame is updated as techniques improve, but the quasars themselves remain as stable anchors, immune to the local motions of our galaxy. The tie between Earth and the ICRF is direct. Every VLBI measurement encodes not only the position of the quasar, but the orientation of Earth at the time of observation. As the planet spins, its rotation carries the telescopes around, changing the timing differences. From this, Earth's rotation rate and axis orientation can be measured to astonishing accuracy. The length of day is known to within microseconds, and polar motion to centimeters, all because quasars provide the fixed backdrop. The result is that Earth's motion is described not just relative to its own surface or the solar system barycenter, but relative to the universe itself. This cosmic tie has practical consequences. Spacecraft navigation, for instance, depends on knowing Earth's position relative to distant objects. When a probe like Voyager or New Horizons communicates with Earth, the timing and direction of its radio signals are corrected using the ICRF. Without this frame, the spacecraft's position could drift by thousands of kilometers. With it, trajectories can be plotted across billions of kilometers with confidence. Even the tiny adjustments needed for planetary flybys depend on this inertial scaffold. The precision of VLBI also reveals the limits of the notion of fixed stars. For centuries, the phrase meant that stars were immovable, but VLBI shows that even quasars are not perfectly fixed. Some display structural changes in their radio jets, which shift their apparent positions by micro-arcseconds over years. Others brighten or fade, altering their signal quality. To maintain stability, astronomers carefully select the most reliable quasars, monitor them continuously, and update their positions. The frame is not static but maintained, a living structure built on ancient light. Yet despite these subtleties, the ICRF is the closest humanity has come to a true inertial frame. It provides the axes against which all other motions are described. Earth's precession, nutation, and wobble are measured relative to it. The solar system's barycentric orbit is tied into it. Even galactic and extragalactic studies depend on it, because without a fixed reference, the motions of stars and galaxies would blur into uncertainty. The ICRF is the ruler of motion on cosmic scales. What emerges from this is a new kind of humility. Earth's location is no longer defined by itself, by the sun, or even by the solar system. It is defined by light that has traveled for billions of years, emitted by galaxies whose shapes have changed since the first humans walked upright. To say where Earth is today is to tie ourselves to that ancient light, to become part of a cosmic web that stretches far beyond our own galaxy. And this in turn raises new questions. If even quasars can shift subtly, what does it mean to claim an exact frame? If the universe itself is expanding, is the ICRF truly fixed, or is it only fixed within the assumptions of relativity? At the edges of precision, even the inertial frame begins to blur, preparing us for the deeper challenge of relativity itself. The act of anchoring Earth to quasars might seem like the end of the journey. After all, what could be more stable than objects billions of light years away, shining steadily across cosmic time? And yet, when precision becomes extreme, even quasars reveal their imperfections. Radio jets can shift subtly as matter streams from their central black holes, changing the apparent position by micro-arcseconds. Some quasars brighten or fade, affecting the clarity of their signals. Others show tiny motions caused by gravitational lensing or by the structures within their host galaxies. The ICRF must therefore be maintained like a carefully tended garden, with new quasars added, unstable ones monitored, and positions recalibrated regularly. This maintenance reveals an important truth. No frame is ever absolute. The ICRF is as close to fixed as humanity can make, but it is still a construction, a network of agreements, refined by measurement. It does not exist as a natural object, but as a chosen system, built on the constancy of light speed and the apparent stillness of distant galaxies. Its power lies not in being eternal, but in being stable enough for our needs, accurate enough to guide spacecraft, and precise enough to define Earth's orientation in the universe. Yet there is a philosophical twist. When we observe quasars, we see them as they were billions of years ago. The light that forms the ICRF left its sources long before Earth even formed. The anchors of our coordinate system are relics of the distant past. We do not know what those galaxies look like today, or even if they still exist. In this sense, our inertial frame is built on ghosts of light, an ancient scaffolding frozen in time. But for us, here and now, those ghosts provide the most stable anchors possible. They remind us that exactness is always contextual, always tied to what can be measured. The reliance on quasars also ties our position to relativity. To define their coordinates, astronomers must account for the bending of light by gravity, the expansion of the universe, and the relativistic transformations between frames. Even the act of saying a quasar is fixed means assuming a cosmological model, in which distant galaxies move with the flow of expansion, but not with local proper motion. The ICRF is thus not just a geometric grid, but a relativistic construct, woven into the fabric of space-time itself. In practice, this makes the ICRF indispensable. It ties together the terrestrial frame where GPS operates, the celestial frame, where Earth's wobble is measured, and the barycentric frame, where planetary motions unfold. Every transformation between these systems passes through the quasars. They are the silent arbiters of exactness, the final court of appeal when disagreements arise. If two observatories measure Earth's rotation differently, the quasars decide who is correct. If two spacecraft trajectories diverge, the quasars anchor the correction. Their light, ancient as it is, governs the present. The result is a paradox both humbling and empowering. Earth's place in the universe is known with extraordinary precision, down to millimeters on its surface and meters in its orbit. Yet that precision rests on a frame built from distant galaxies, observed through telescopes, interpreted through models, and constantly corrected. Exactness is real, but it is conditional. It is not the universe declaring where Earth is, but humanity deciding, through consensus and measurement, what exactness shall mean. And this realization brings us to the threshold of relativity. For in relativity, there is no single, universal frame. Position depends on the observer, on the motion and the gravitational field, on the coordinates chosen. The ICRF is inertial only within the assumptions of general relativity. It is not absolute space, but a carefully constructed convenience. To speak of Earth's exact location, we must now confront the fact that in Einstein's universe, simultaneity is relative. Distances depend on curvature, and time itself is not universal. Thus, as Chapter 7 closes, the story shifts from cosmic anchors to the relativity that governs them. Earth's position has been tied to quasars, to the deepest beacons we can see. But the very act of calling them fixed hides the relativistic complexities that shape our understanding of space and time. The next chapter will open those complexities, showing how special and general relativity reshape the idea of an exact location, and why precision must always bow to the structure of space-time. When Isaac Newton described space and time, he imagined them as a grand stage, infinite and absolute. Events occurred in space, which was fixed, and unfolded in time, which ticked evenly everywhere. Within this framework, location was straightforward. Earth had a position, defined against an eternal backdrop, and motion was measured as change against that backdrop. It was a picture of certainty, comforting in its simplicity. Einstein shattered that comfort. In special relativity, time and space are not independent, but woven together into space-time. Distances and durations depend on the observer's motion. Two events that are simultaneous for one observer may not be simultaneous for another. A ruler shrinks when carried at high speed. A clock ticks more slowly when moving. The stage itself bends to the players, and the idea of an absolute position evaporates. Location becomes a matter of perspective, defined only within a chosen frame. This shift affects even the most practical systems. Consider GPS satellites, orbiting Earth at several kilometers per second. Their onboard clocks run faster than clocks on Earth's surface because gravity is weaker at their altitude, yet they also run slower because of their orbital speed. The two effects nearly cancel, but not quite. If uncorrected, the difference would cause navigation errors of kilometers per day. Instead, the system applies relativistic corrections so that time remains synchronized. Position itself depends on relativity. Without Einstein, your phone could not tell you where you are. General relativity deepens the challenge. In Einstein's vision, gravity is not a force pulling at a distance, but the curvature of spacetime itself. Mass and energy tell spacetime how to curve, and spacetime tells matter how to move. Earth does not orbit the sun because of a force tugging across space. It follows a curved path in spacetime shaped by the sun's mass. Light itself follows these curves, bending around stars and black holes. Distances are not fixed, but shaped by geometry that depends on matter. This means that even the act of measuring Earth's orbit is laced with relativity. When we say radar signals take a certain time to bounce off Venus, we must account for the Shapiro delay, the extra time added because light passes near the curved spacetime around the Sunday. When we calculate the orbit of Mercury, we must include the precession caused by spacetime curvature, or our predictions will be off by tens of kilometers per century. Without relativity, our maps of Earth in the solar system would drift into error. With relativity, they remain sharp. But relativity also undermines the dream of absolute exactness. In curved space-time, the distance between 2 points depends on the path chosen. The time between 2 events depends on the observer's motion. There is no single universal map that everyone shares. Instead, there are coordinate systems, each useful in its context, but none privileged as absolute. Astronomers use the barycentric celestial reference system for planetary motions, the geocentric celestial reference system for Earth, and the terrestrial frame for life on the surface. Each is consistent, each is precise, but none is eternal. This realization alters the question itself. To ask exactly where is Earth in relativity is to ask where, in which coordinates, at which moment, as seen by which observer. The answer is not a single set of numbers, but a carefully chosen frame, with corrections for gravity and motion. Exactness becomes operational. It is defined by what measurements are needed, what system is used, and how relativity is applied. The profound irony is that relativity, which removes absolutes, has also given us the greatest precision. By understanding time dilation, we can build atomic clocks that remain synchronized across continents. By modeling space-time curvature, we can track spacecraft across the solar system. By applying relativistic corrections, we can measure Earth's orbit to meters and its surface to millimeters. Relativity turns uncertainty into clarity, not by restoring absolutes, but by embracing their absence. Yet for all its power, relativity complicates the story of location. It reminds us that maps are choices, that positions are defined by frames, and that the universe itself offers no single stage upon which Earth can be pinned. The next step is to explore these consequences in detail: how time dilation reshapes clocks, how gravitational redshift alters signals, and how coordinate systems like the barycentric and geocentric frames express Earth's position differently. The pursuit of exactness now enters its most subtle phase, where physics and philosophy intertwine. Relativity is often treated as an abstract concept, a set of equations written on chalkboards, or a theme for science documentaries. Yet it is woven into the practical machinery of modern civilization. Every time a signal crosses the sky from satellite to receiver, or a beam of light is timed in a laboratory, the fingerprints of relativity are present. If we ignored them, our carefully constructed maps of Earth would dissolve into errors. The most familiar example is GPS. Each satellite in orbit carries atomic clocks that must remain synchronized with clocks on the ground. But because of special relativity, the motion of the satellites makes their clocks tick more slowly than those on Earth's surface. Because of general relativity, the weaker gravity at orbital altitude makes their clocks tick faster. The net effect is that the satellite clocks gain about 38 microseconds each day compared to those on Earth. That tiny difference translates into a positional error of several kilometers if uncorrected. To maintain accuracy, the system adjusts the rates of the onboard clocks before launch and applies continual corrections afterward. Relativity is not optional. It is the reason GPS works. The same principle applies to deep space missions. When signals are sent to a spacecraft at Mars or Saturn, they travel through curved space-time, shaped by the sunday. The delay imposed by that curvature, known as the Shapiro delay, can add hundreds of microseconds. If ignored, it would shift the inferred position of the spacecraft by kilometers. Instead, mission planners calculate the effect precisely, using Einstein's equations to remove the delay and recover the true geometry. By doing so, probes can be guided through narrow gravitational assists, threading invisible corridors of space-time with meter-scale accuracy. Even within astronomy itself, relativity is essential. When light from a distant quasar is timed to establish the International Celestial Reference Frame, it passes through Earth's gravitational field, where its frequency shifts slightly. This gravitational redshift must be accounted for to keep clocks consistent across observatories. Likewise, when pulsars are timed to search for gravitational waves, corrections must include both Earth's orbital motion and the relativistic effects of curved spacetime near the Sunday. Without these corrections, the faint signals of ripples in spacetime would be buried in noise. These adjustments might sound like technicalities, but they reshape the very definition of coordinates. Astronomers distinguish between the barycentric celestial reference system, centered on the solar system barycenter and used for planetary motions, and the geocentric celestial reference system, centered on Earth's center of mass. Both are defined within general relativity, with specific conventions for how time and space are measured. Transforming between them requires precise, relativistic models. Even the act of saying Earth is at a given coordinate at a given time is inseparable from these frameworks. The importance of relativity grows as precision improves. In the 19th century, when positional errors of arcseconds were common, relativistic corrections could be ignored. In the 20th century, with the rise of radar ranging, they became noticeable. Today, with millimeter geodesy and nanosecond timing, they are indispensable. A single uncorrected relativistic effect can overwhelm all other sources of error. As technology sharpens, relativity moves from theory to necessity. This reliance also underscores a philosophical point. Relativity tells us there is no single, universal time, no absolute simultaneity. And yet, we create practical timescales like coordinated universal time, built from atomic clocks and corrected by relativity, to give the illusion of universality. We define coordinates in frames like the ICRF or the barycentric system, knowing they are conventions layered upon curved spacetime. Exactness in this view is an agreement to use a chosen system and to apply relativity consistently. It is precision built on consensus, not absolutes. What emerges is a paradox both scientific and human. The very theory that removed absolute space and time has allowed us to know Earth's location more precisely than ever. By accepting that there is no single map, we build better maps. By acknowledging that time is relative, we synchronize clocks more faithfully. By modeling the curvature of space-time, we measure Earth's orbit with unprecedented clarity. Relativity does not erase exactness. It redefines it in a richer, more subtle way. And this redefinition prepares us for the next step. To speak of Earth's location under relativity is to enter a world where coordinates depend on choices, where distances and times are contextual, and where precision is always finite. The final part of this chapter will explore how far that precision can go, what limits persist, and how the interplay of relativity, measurement, and philosophy shapes the very idea of being exact. Relativity forces us to accept that exactness has boundaries. In Newton's world, there was always a true answer, a set of coordinates that defined Earth's location once and for all. In Einstein's world, the very notion of where becomes conditional. It depends on the observer's motion, the gravitational field, and the chosen coordinates. The question shifts from where is Earth to where is Earth, according to this frame, at this moment, for this observer. This does not mean that precision collapses. On the contrary, relativity gives us tools to sharpen it. By modeling space-time curvature, we correct for gravitational delays. By accounting for time dilation, we synchronize clocks across satellites and continents. By defining coordinate systems within relativity, we compare measurements made in different places and times. But precision always lives within the frame, never outside it. There is no cosmic ruler that declares the one true location. There are only carefully constructed systems, each valid within its context. The dependence on frames becomes clearest when comparing geocentric and barycentric systems. In the geocentric frame, Earth is the center, and satellites orbit around it. In the barycentric frame, Earth is one planet among many, circling the solar system's balance point. Both are true, but they give different coordinates for the same event. Transformations between them require relativistic corrections, and both are embedded within the larger structure of spacetime. To speak of exactness without naming the frame is meaningless. Even the idea of simultaneity dissolves. Imagine two signals, one sent from a satellite and one from a ground station. In one frame, they occur at the same time. In another, moving at high speed. One precedes the other. Which is correct? Both, depending on perspective. There is no universal now that spans the cosmos. The concept of where Earth is now depends on the clock and the frame chosen. For most purposes, we adopt conventions like coordinated universal time and barycentric dynamical time. But these are human constructs, agreements layered on relativistic reality. These subtleties matter not only for philosophy but for science. When astronomers detect gravitational waves by timing pulsars, they must model Earth's motion and the curvature of space-time across the solar system. When physicists compare atomic clocks on Earth and in orbit, they test gravitational redshift at the part per billion level. When engineers guide spacecraft through planetary flybys, they account for time dilation and Shapiro delays. In each case, relativity is not an abstract correction, but the foundation of precision. And yet, there remains a horizon we cannot cross. Measurement always contains noise from instruments, from the atmosphere, from quantum fluctuations. Models always contain